Hi everyone, welcome to Ancients. In our previous video, we explored the brush self-excited alternator. If you haven't watched it, check them out on the cards. Today, we'll continue by exploring the brushless self-excitation system and permanent magnet generator. In brushless excitation, current is supplied to the rotor without any physical contact or wearing parts. How is it possible to supply current without any physical contact? If we carefully observe the generator, power is generated in the rotor without any physical contact. The same principle is used in brushless excitation. Power is generated in windings mounted on the exciter rotor, and a separate exciter stator is fixed to the main case of the generator. DC power from the AVR is supplied to the exciter stator to generate magnetic field. The exciter stator winding is done similar to the main alternator rotor, where coils are wound in alternating clockwise and counterclockwise directions to create alternating magnetic poles. The exciter rotor coil winding is done similar to the main alternator stator, where 3 coils are positioned 120 degrees apart. When the rotor rotates, it cuts the alternating magnetic fields produced by the exciter stator. The exciter rotor coils generate 3-phase AC current, but the main alternator field requires DC current. Therefore, rotating rectifier diodes are used to convert AC to DC current. These rectifier diodes are mounted directly on the exciter rotor and rotate with it. Full-wave bridge rectification is used to convert AC to DC current. The system uses 6 diodes, 3 positive diodes and 3 negative diodes, arranged in a 3-phase bridge configuration. One end of the 3-phase exciter coils are connected in star configuration, neutral point, and the other ends are connected to the rectifier bridge. Each phase connects to the junction point between a positive and negative diode pair. If we consider how AC current is converted to DC, positive half cycles remain positive, while negative half cycles are inverted to positive by the rectifier diodes. By using 3-phase full-wave rectification, the ripple in DC current is significantly reduced compared to single-phase rectification. The graph shows how AC current is converted to smoother DC current. For additional ripple reduction and protection against voltage spikes, a metal oxide varistor, MOV, is connected across the DC output. The MOV acts as a surge suppressor, clamping excessive voltages and protecting the rectifier diodes and main field winding from damage. The challenge is providing initial voltage to the exciter stator at startup. Relying solely on residual magnetism can cause problems with voltage buildup. Instead of self-excitation, a separate independent system is used, the permanent magnet generator, PMG. The PMG is mounted on the same shaft as the main alternator but operates independently. The PMG rotor consists of permanent magnets, typically neodymium magnets, mounted on the rotating shaft. These permanent magnets create alternating magnetic poles that face the stationary PMG stator windings. As the rotor rotates, the moving permanent magnets cut through the PMG stator windings, generating clean 3-phase AC electricity. Now let's examine the component that monitors and controls all these systems, the automatic voltage regulator, AVR. The most important function of the AVR is to automatically control alternator voltage and maintain constant output at the appropriate voltage level, regardless of the current being drawn by the load. This ensures that connected equipment receives a stable power supply. The AVR receives 3-phase electricity from the PMG. The AVR converts this 3-phase AC electricity into regulated DC current using internal rectifier circuits. This converted DC current is supplied to the exciter stator field winding. 2 terminals from the main alternator output are connected to the AVR for voltage sensing. The AVR continuously senses the voltage from the alternator terminals and compares it to a stable internal reference voltage. When it detects a discrepancy, the AVR adjusts the exciter field current by increasing or decreasing current flow to the exciter stator. This adjustment results in either higher or lower voltage at the main stator terminals, bringing the output back to the desired level. The brushless excitation system with PMG provides several advantages. Constant power supply to the AVR regardless of load conditions, no residual magnetism dependency for startup, faster voltage recovery during load transients, and elimination of carbon brushes for maintenance-free operation. If you found this video helpful, give it a like and don't forget to subscribe.